going to relate this idea of kinetic molecular theory to the way that gases behave. So the gas laws, for instance, Boyle's law. As pressure increases, let's think about it the other way, I'm sorry. Let's say as volume increases, what happens to the pressure of a gas? So as the volume that gas is occupying increases, what happens to the pressure of that gas? Well, it decreases, right? They are inversely proportional. And so today what we're going to do is we're going to talk about how does kinetic molecular theory explain that. All right, so yeah, let's start with that first one. Let's start with this idea of, first of all, pressure and volume. Okay, so as let's say we decrease the pressure, we decrease the volume that a gas is occupying. And we will do that actually as a demo or a little activity in class so that you can really feel this. If we decrease the volume that a gas is occupying, what then will happen to the pressure of that gas? Well, the pressure is going to increase. Okay, we know this from the gas law. But why is that the case? Well, if we can imagine, keeping in mind that what is pressure at the molecular level, you guys, it is the collisions of the gas particles with a surface. And so the more often and more forceful the collisions, the greater the pressure. The less often the collisions, the lesser amount of pressure. And so a decrease in the volume of a gas, okay, so if we're compressing it, means that the gas particles are going to hit the wall of the container more often, and that is going to increase the pressure. So whenever we're talking about changes in pressure, increasing pressure, decreasing pressure, you guys, we need to talk about that in terms of the number of collisions of those gas particles with the container that they're in. The more collisions, the greater the pressure. The less the collisions, the lesser the pressure. So if you squeeze down something's volume, of course, it doesn't have as far to travel to collide with the container, the inside walls of the container, and so the pressure is going to go up because it's going to collide more often with the walls of the container because it doesn't have as far to go. Okay, what is next? We have pressure and temperature. Now, let's keep in mind, what did we say temperature is, you guys? Well, it is the average kinetic energy of the particles that make something up. So, of course, if you are raising the temperature of something, that is raising the kinetic energy of the gas molecules that make it up, and that's increasing their speed. And if they're moving faster, they're going to collide more often. Vice versa, if you cool them, they're moving slower, they will collide less often with the inside surface of their container. So, when gas temperature increases, the speed of the particles increase. Now we know, you guys, okay, this is kinetic energy, the kinetic energy, but in this case, mass isn't changing, so, it's the same gas molecule at the time. So it's easy for us to think of it in terms of speed, and it's appropriate, actually. So when gas temperature increases, the speed, technically the kinetic energy of particles increase. So they are hitting the wall of the container with greater force and greater frequency. why is this greater force? That greater inertia, right? So if the volume remains the same, we're not changing the size of the container at all, then that means that we're going to have an increase in pressure. So when temperature increases, the speed of particles is going to increase as well, and they will hit the walls of their container more often, and we see it as greater pressure. Volume and temperature. Okay, so this one is a little bit trickier. So let's go. I'm going to go ahead and read it, and then I'll talk about this. So when gas is heated to a higher temperature, the speed of the particles increase. Thus, they hit the wall of a container more often with more force, right? So higher temperature means higher kinetic energy. And so they're moving faster. So they hit the wall of the container more often with more force. Now, if we are in a situation where we want to keep the pressure constant, the only way that that can happen is if the volume of that gas increases. This one's a little different, because in this one we do really have to take into account, we're keeping the pressure constant, keeping equal pressure inside, outside. Then if we're in a flexible container, you guys, like a balloon or something like that, or a tire, right, the volume is going to get larger, smaller. Okay. Volume and number of moles. So if we increase the number of gas molecules at the same temperature, it will cause the pressure to increase. Okay, so if we're in a situation where the pressure is kept constant, again, you guys, we're in a flexible container. Both of these things with volume, volume can only change. Volume can only change if a gas is in a container that's flexible. So if the pressure is going to stay constant, the volume must increase with the addition of more molecules. The volume of a gas at constant pressure and temperature depends only on the number of particles. N, number of moles, you guys, that's what that is, N. Not the particle sizes or volume. Okay, so we never take into account the volume of the gas particles themselves. Why? Because their volume is so small compared to the space between particles. The particle volume itself is negligible. So we don't ever think of the gas as taking up part of the volume of the total container, because the sizes are very, very tiny. So we don't ever think about large gas molecules versus small gas molecules, and them actually occupying, taking up part of the room of the total volume. I'm saying this because we're going to have problems where you're going to try to do that in the future, and so I'm kind of just trying to lay the neural network of this more than anything. So because their volume is so small compared to the space between particles, particle volume itself is negligible. Now, there are going to be conditions in the real world for engineers where this isn't the case because the volume that a gas is occupying is so tiny that the size of the particles actually do become important. And we will talk about that at the very end, non-ideal behavior. But for what we're doing, we just assume that gas molecules are so tiny that we don't really need to take them into account as taking up a large amount of space that the gas is occupying. Okay, and last but not least, gas mixtures. Total pressure exerted by a mixture of gases is the sum of the pressures of the individual gases. Gas particles are independent of one another, and the volumes of the individual particles are unimportant. The identities of the gas particles don't matter either. They act as one ideal gas. So, because their volume is so small, there's so much space between them that it's not until we squeeze gases down to a very, very, very tiny volume that their volume and the kind of molecule that they are even come into play at all. That in general environmental conditions that we will be dealing with, the identities of gas particles don't matter. That mixtures of gases, we just think of this thing as being one ideal gas. And we don't have to take the pieces, the components into account. That's not the same with a liquid. That is not the same with a liquid at all. All right. So, we are going to go over again and again how we explain gas laws in terms of kinetic molecular theory. But at least now you've got it all written down. All right, that's it.